You know, as far as actual implementation, well, it's high voltage, you know, it's the direct and indirect issue. There are a lot of different things that make it different than a diode, but at the fundamental level, it's a diode. Okay, so this is how a diode is shown in tube schematic notation. Works the same. Current flows in one direction. Typically, when we talk, you know, what do we use a diode for? We use it for rectification. We take our input AC from the outlet. With tubes, we often step it up to a higher voltage. We then want to rectify it to DC to get our power supply around.
What kind of voltage is typical?
Tubes, it depends on the amp. Like a smaller amp like that, 125, 250. You know, full-size Marshall, 400 or 500 volts.
Yeah.
Yeah. Some even higher. So like some of the more advanced tubes I mentioned earlier, the later level, you can see voltages in 600 volt range easily. And of course, not only do you have to worry about the voltage on the tube, but all the capacitors in the circuit have to be high voltage caps. So the rectifier tube converts the 50 hertz AC to give us our DC power supply rails. Now, I mentioned that you couldn't have a really densely integrated circuit with tubes, but you did have certain degrees of integration. So one of the things they would do is, instead of having just a single diode, you could have a full-wave rectifier, which is effectively 2 diodes in one package. Much like nowadays, you can go to Radio Shack and buy a bridge rectifier, which is 4 diodes, you know, arranged in a bridge. You can get similar things with 2 diodes. So you can do full-wave or half-wave rectifier, and some of them have a common cathode, or some of them can have 2 different cathodes. And again, you do directly or indirectly heat. So to get a full-wave rectification, you generally use single 2-plate tube with a center tap power transformer. Okay, remember we looked at transformers a few weeks ago. So center tap just means if that's your input, that's your output. You take the center tap, you reference that to the ground, and then you use the 2 different, you tie the 2 different phases to the 2 different plates. You know, and that's how you get your current out. Okay. Some common tubes, we'll talk about 35W4. That's an indirectly heated half-wave rectifier, very common in small amps, and we'll talk about why later. You can kind of tell from the number if you know a little something about tubes. If not, I'm going to tell you about those when we talk about widowmaker amps. 5Y3 GT, super common tube available in high power and low power amps. I believe the Fender Champ I brought into demo does use the 5Y3 GT rectifier. All right, so tubes are good, tubes are wonderful. I mean, they were a huge advance, but there are some issues. Not all the electrons float to the anode, right? You got this cloud of electrons around the cathode, and you put a positive voltage to try and attract some. Well, some still stay around the cathode, some of them aren't drawn. So those stay in the air in space, and some, you know, lose energy and return to the conductor, or return to the cathode. Okay. But the ones in the air we're interested in, the space charge has a repelling force of other electrons. You've got a cloud of electrons, well, other electrons are going to be repelled by it. So we'd like to reduce the space charge. How do we do that? Well, we can create a higher plate voltage and effectively suck more of the electrons across the vacuum. Or we can reduce the distance, and then, again, increase the force that pulls on those electrons. And these are different variations that are used in the tube. At some point, we hit the saturation point. And at that point, effectively all the possible electrons flow from the cathode to the anode. And that's called the emission current. That's the maximum current you can get through the tube. And remember that phrase, emission current. We'll see emissions later. All right, so the diode's cool. It allows you to do something, you know, allows you to do solid state rectification. Or not solid state, well, I don't know if tubes are solid, considered, not really considered solid state, no moving parts, we'll say. So now we come to the triode. And the triode is really something because now we add this extra layer in the middle, right? So we've got a positive voltage here, we've got a source of electrons here. We put a grid in the middle. And this grid, again, is implemented as a spiral cage. And the idea here is that if we put nothing on the grid, right, the electrons see the positive voltage and they get attracted. If we put a negative voltage here, the electrons see that negative voltage. They don't get attracted to the plate. All they see is all they sense is the grid. So the grid allows you to control how much electrons go through. It allows you to be a solid or a non-moving part switch, and it allows you to be an amplifier. For the first time, you've got the ability to take a low-level signal and amplify it to create a certain current. And you drive that current through a resistor, you get a higher level signal.
What's to stop electrons going into the grid and current flowing through there?
They can. And that's what we were talking about as far as Class AB1 versus Class AB2 power amps. Sometimes they do flow there. For the most part, though, the grid is widely spaced, so electrons, they don't hit it as much, you know, because the windings are spaced out. And also, the voltage there, usually the grid is held negative to the cathode. So they don't want to go there.
So it's kind of like a PNP, right? You know, like a base current. You get like a base current coming out kind of.
You typically don't. It's kind of more like a JFET.
Really?
That if you bias it the right way, you shouldn't get a current. Unless you're doing this, you know, the class, I think Class AB2, where you do get the current.
Okay.
So, yeah. So, like I said, it's negative relative to the cathode. So that's where it really doesn't flow. Okay. So getting back to what it's supposed to do, we call it the control grid because it controls. So if it's very negative relative to the cathode, no current flows. The electrons effectively don't see the plate. As it becomes more positive, more electrons are sent to the plate, and they hit the plate and get absorbed by the plate, and you see how it can be used as an amplifier at that point, because you just vary the signal in the control grid, and you vary the amount of electrons that get there. And it's very similar to a FET in that it's a voltage-controlled current source, right, as opposed to BJT, which is current. This is good. This is amazing. This is 1907. This is a huge advance in electronics. You know, there are still some issues. You still got those interelement capacitors. We talked about you know, the problem with the diode. Well, there are problems with the triode. You have a grid to plate capacitance, right? And you've got this flat piece of metal next to this grid that looks like kind of like a parallel plate capacitor. There are problems. And you can get coupling between the elements. So if you've got coupling, you can get a feedback path. So if you try to create something that's too high gain with the triode, you create this feedback path and it oscillates, it doesn't work. You can have problems. Okay, common tubes. There are actually very few triodes that I know of that are just strictly a triode. What you find usually are triodes integrated with other things. And very often only the triode is used. For instance, the 6AB6 is a fairly common audio tube and amplifier. It's used in a number of little amps similar to the Fender Champ, but not particularly that Fender Champ. And they just use the triode. It actually has a twin diode in it. They don't use it. 12BF6 the same way. That's a medium U triode with a source.
Mu.
We'll get to that. It's amplification factor. I'll get to the actual definition. Okay, and then the call out on the top we talked about before. What solid state device has a triode? The MOSFET, right? You have the triode region, and it resembles the behavior of a vacuum tube triode. Conceptually, there's no difference between a triode and a twin triode, but as things got more complex, just like with the diodes, they wanted to